So yeah, Eknath, you can start.
Okay, so thank you very much. I believe you can see me even though I can't see myself, but you can also see my paper. So that's great. So it's a pleasure to come back here and speak at IIT Guwahati. Even though it is online, I spoke there on a very similar topic about 12 years ago. So in fact, as a reference for these lectures, let me just say at the beginning that the Guwahati lecture notes from the 2008 school on the Osama main conjecture. There is a chapter on lambdatic forms there with me and some of my ex-students, Devargavaji and Narsima Kumar. And you can look at that from time to time, but I will give more references as we go along. Okay, so let us first start with classical modular forms. One of the advantages of speaking second is that I can go a bit fast here. So tell me if there are too many shadows. I put some light on my dock camera on also. So I'll turn it off. Is this better or this better? This is number 2. This is number 1. So anyway, I'll keep it on now. Right now it's on. So this is the first time I'm giving a lecture like this with this dock camera. And the paper will move around a bit, but hopefully not too much. So let's start with classical modular forms. So Professor Ramki gave a nice introduction to them, and I will recall some notation, and maybe I'll skip a few things since he did many things. So let k be an integer greater than or equal to 1, and be another integer greater than or equal to 1, and let chi be a Dirichlet character. So integer, and this is a Dirichlet character. So a homomorphism from Z mod n star to C star. So as we all know, and as was recalled just an hour and a half ago, or an hour and 45 minutes ago, a modular form of weight k, level n, and character chi is a holomorphic function f from the upper half plane to the complex numbers. So it's a function on the upper half plane.
So it is going below the camera, sir.
Oh, it's going below the camera. Great, great. Please tell me, especially on my first day. Maybe I'll zoom up a bit. Let me move the camera up. I hope it doesn't get too small though. Okay, I think I can only move the paper up, so I'll have to just put it to the desk. You can see the page now? Okay, so
yeah, we can see.
Yeah, okay, so it's a function from the upper half plane such that f of gamma z, this was written as az plus b over cz plus d. So we have 2 points on the upper half plane, z and gamma z. Gamma is a matrix, a, b, c, d in some group, which I'll write down in a second. So this function satisfies lots of very nice symmetry properties. It's rather remarkable that such functions should even exist. There are infinitely many conditions that this function has to satisfy. So this is for all matrices gamma, a, b, c, d in this subgroup gamma naught n, which is a subgroup of the 2 by 2 matrices with integer entries and determinant 1, SL2Z, with the condition that C is common to 0 mod n. So all such functions satisfying these symmetry properties, and we require that f is holomorphic at the cusps. Okay, so maybe a brief recall on that. If you take the matrix gamma to be 1, 1, 0, 1, this particular matrix, then you see that this condition here becomes something very simple. It's just f of z plus 1 chi of 1 is 1, cz plus d, all this is just 1, so it's just f of z, right? So that means f is actually a function of q, where q is equal to e to the 2 pi lz. Yes, I'm going to make an arrow here so these matrices act. So this upper half plane gets replaced by the punctured unit disk. Okay, so this is the q variable and this is the z variable. And again, I think you can barely now see the bottom of my page, which is not good. Maybe I'll go to the topmost version, but I hope it's not too small. Anupam, is it too small now or is it okay?
Yeah, it is fine. It is fine.
I've gone to maximum zoom now. I mean, zoom
Yeah.
out. Okay, so f of z is qz. F of z is f of q, with q in the unit disk. And we require that this point here, the origin, so infinity here, which is way off over there, becomes the origin, and we require that 0 is a removable singularity. So of course it's holomorphic everywhere in the punctured unit disk, but at the point 0 also, you can fill it in and make it holomorphic. Okay, and so it has a Q expansion, and we're requiring it to be holomorphic there. So this is a condition, n equals 0 to infinity. This is the Taylor expansion at the point origin. 0 is a removable singularity. Okay, so there's a similar condition at all the other cusps, and the space of such forms are called modular forms. And if this an here is 0 at n equals 0, so it vanishes at q equals 0 or z equals infinity, then it's beginning to look like what is called a cusp form, but you also require that these similar q expansions at the other cusps also vanish. So the leading term a0 at the other cusps is also 0. Okay, so maybe I'll write some things here. Say f is a cusp form. This is a modular form, cusp form, if f vanishes at all the cusps. Okay, and then finally, I'll try and squeeze this notation in. I hope you can see it. Okay, I'll lift the page, lift the camera a bit. So let mk and chi, respectively sk and chi, is exactly Professor Ramke's notation and all the notation in most books, be the complex vector space of all modular cusp forms, modular forms or cusp forms. Okay, so you can add two cusp forms and you can multiply cusp forms by scalars. So the space sk and chi is a complex vector space. It turns out to be finite dimensional, both these spaces. Okay, so this is, I think everybody knows well. Okay, maybe I'll move this from the, you can go back and ask me if you want a particular page put anywhere. Okay, so some more notation, which essentially came up in the last lecture. So let us say that f is normalized if the first Fourier coefficient is 1. So first in the sense a1, not a0. Okay, so this a0 may not be 1. It may be something non-zero, but not 1. But normalized is the second Fourier coefficient if you want, but a1 is 1. Say f is an eigenform if it's a common eigenfunction of all the Hecke operators, which came up in the last lecture. Okay, so lambda n is a complex number, often an algebraic number, often an algebraic integer even. So Tn of f is the lambda n times f for all natural numbers, n equals 1. And Tn is the Hecke operator.
Excuse me, sir.
Yes.
Can you please write a bit larger?
Okay. Okay. Yes. And finally, F is a new form. Maybe I'll go back and zoom in on this page. Does this help?
Yes, sir. Yes, sir.
If F is orthogonal to all old forms. Okay, so without getting into too much details, you can have a modular form of smaller level, G, and then for each divisor D of n by m, m is also a divisor of n. Simplicity in this notation, you can push forward this function, g of z by g of dz, and that becomes a modular form of level n. And when required, so these are by definition the space of all forms. And then under the Peterson inner product, you require that this function f is orthogonal to all the old forms. So it's genuinely of level n. It's not coming from smaller level. Okay. So I won't write here under the Peterson inner product, but this is under the Peterson inner product, which was defined last time. And finally, we require that f is primitive. Sorry, we say that f is primitive if all of the above hold. So I don't want to say normalized form, eigenform, and new form each time. So primitive form for me will be a form which is normalized, an eigenform, a new form, all these things. Okay, so we will mostly work with primitive forms, though there's a slight subtlety in the theory of lambdatic forms, which I'll get to in a second. Okay, so here's an important fact, which I will only come to in the last lecture. Let me state it up front. If f is primitive, Gus form, then there's a Galois representation attached to f. Rho f from the Galois group of Q is a continuous irreducible Galois representation to GL2 of a p-adic field. So here, what is this KF? KF is it's a primitive form. So in this case of a primitive form, all the Fourier coefficients, these are called Fourier coefficients, these AAN, they're really Taylor coefficients, but for some reason they're called Fourier coefficients. So all the Fourier coefficients, when you tack them onto Q, even though there are infinitely many of them, they still generate a finite extension of Q. So it's a number field. And you fix a prime P. So this is a p-adic Galois representation. And Weierstrass P is a prime in the number field lying above the prime P. And this KFP is the p-adic completion of KF at the prime P. Okay, so this is a p-adic representation. It's taking values in a finite extension of the p-adic number field QP. Okay, such that the trace of rho f at the Frobenius element at L, prime L, is nothing but the Lth Fourier coefficient. And similarly, the determinant is given by a simple formula involving the Nebentypes chi, the character chi, and the weight k for all primes L not dividing NP. Okay, so there's this Galois representation. So I just want to introduce this right now, but I will come back to it later in the fourth lecture. But this is something that one should keep in mind. It is sort of perhaps the main object to introduce lambdatic forms, is to study these classical Galois representations. Many classical problems in Galois representations can be studied by lambdatic forms and lambdatic Galois representations. So now let us turn to some examples of modular forms. Modular forms and Gus forms. And everybody gives the same examples, and so will I. But I need to introduce the notation. So the first are really genuine modular forms, the Eisenstein series. And as Professor Ramke said, usually you have to assume that n is, sorry, k is bigger than or equal to 4 here. I'm going to assume n is equal to 1 at the beginning, just in the first few minutes, and then I'll move to general n, and the Neyman type is trivial. And then he defines some Eisenstein series, Ek, and then up to a normalization. Oops, it's gone off the page. He says something if it's not going off the page. Yeah, so Ek, which was the Eisenstein series defined in the previous lecture, up to some fudge factor, up to some constant. It is exactly this. Sorry. So the constant term A naught is zeta 1 minus k by 2, which is just a Bernoulli number, minus bk over 2k, whereas the Q expansion is very, very well known. It's a modular form of level 1 and trivial character. Okay, and this is just the sum of divisor function. I think this was also hopefully defined in the last lecture. I guess it wasn't. Let me just do it. Divisor function, sum of the k minus first powers of the divisors d of n. Okay. Okay. So this is something that you have definitely seen perhaps before, but let me make the following remark.
So you have to slide down a bit. I mean, it's not visible. Yeah, okay, fine, thanks.
So for k equals 2, yeah, please keep telling me on every page at the top and bottom, because I'll forget every time. For k equals 2, Ek is not holomorphic. Not a holomorphic function on the upper half plane. It's not purely a function of z. There's some 1 over y terms and things like that. So this is a little annoying, but one can do the following thing. You can cancel off the 1 over y term by looking at a difference of two Eisenstein series. So let P be a prime. And let EKP, you take a difference of two old forms, right? You push forward level 1 to level P. So this is a modular form now. As it turns out to be holomorphic of level P. So for gamma naught P and of level 1. So this thing is actually holomorphic for all k greater than or equal to 2. Okay, so this is maybe one reason to look at the difference of these two Eisenstein series. Is to include the case of k equals 2. But there are other reasons, and I will come to it now. So this Eisenstein series is what is called the p-stabilization of this modular form. So this is for the first time. It's called the p-stabilization of EKP. Okay, so let us now work a bit more generally. I want to do this in the simple setting of level 1, but one can do this more generally. So now let k be even 1, k be greater than 1. Let's fix n in any integer, which is co-prime to p. P is some prime, and chi to be a Dirichlet character. But I'm going to do something a little strange here. Please pay attention here. The conductor of the character is not n, but it's n times p to the r, where r is greater than or equal to 1. Okay, so these are now the starting data. And chi has the same parity as k. That means chi of minus 1 is minus 1 to the k. Chi of minus 1, of course, is plus minus 1, so we're required to have the same parity as k. Otherwise, you get a zero space of modular forms. Okay, so set Ek chi now. I've introduced this character chi, so this is a slightly more general Eisenstein series. You take the Dirichlet function attached to chi and evaluate it at 1 minus k. So if you don't like Dirichlet functions, though they came up in the last lecture, this is something very explicit again. It's a generalized Bernoulli number. I won't define it here, but very similar to the Bernoulli numbers that came up in the last lecture. So minus bk chi divided by 2k, and then the other coefficients in the Q expansion are very similar to what we just saw. So this is now also sum of divisors of n with k minus first powers, but you put a chi of d in front. Okay, so this is now a more general Eisenstein series, and this belongs to the space mk n p to the r chi. Okay, I'll make a small remark here. If chi has level n, so here chi had level npr, but if chi had level n, then in fact this just belongs to mkn chi. Okay, that's just obvious from what I've said here. But that is, so if you don't like the p here, then you can take a character of level n, and then you'll get just a modular form of level n. Okay, so let's look at its p stabilization. Sorry. Let me try something, since it also allows me to slow down. Good. Works, the whiteout. It with an apostrophe s is it is, so not it is, it's p stabilization is the following difference of two old forms. You take ek chi and you subtract off chi p e to the k minus 1 ep chi pz. So here's the old form ek chi pz, and here's the other old form, but just trivially push forward to level p, and you take this difference and there's just a constant, right? And you take this particular constant. So this turns out now to be a modular form in this space. Okay, and its Q expansion is now something quite interesting. It's p deprived. There is a p deprived Q expansion. So what do I mean by that? So it looks something like this. Putting an upper p everywhere. N q to the n. I hope you can see. Otherwise, let me do this. So this is 1 minus chi p, p to the k minus 1, L1 minus k over 2. We had the L1 minus k over 2 before, right? But we multiply it by this fudge factor, 1 minus chi p, p to the k minus 1. Notice that if chi is conductor p, you're not doing anything here. But if chi is of level n, then you're really doing something here. If chi has p in the conductor, chi of p is 0, right? So this was just 1 minus 0, so you're not changing anything. But if chi was of level n, then you're changing something. And this is the sum d dividing n, but now d is co-prime to p, chi of d, d to the k minus 1. Okay, so let me make this remark here. If p divides the conductor of chi, then we haven't done much. Then the p stabilization is just itself. Ek chi p stabilized is just ek chi. Okay, but in general, of course, I mean, you may want to start with the character chi of conductor n and then p stabilize it. So then you have to change, these things have changed a little bit. Any questions so far? So I've not done much. I've just defined Eisenstein series and I've defined the p stabilization of Eisenstein series. Okay, so let me move on. So the second example of modular forms are going to be those coming from elliptic curves, and they're actually going to be cusp forms. Okay, so the amazing thing about modular forms is they show up in so many different branches of mathematics, and the simplest case where they show up in geometry is in the theory of elliptic curves. So let me quickly review this. You can give whole semester-long courses on elliptic curves, but I won't do that, of course. So let us take a cubic equation, y squared equals x cubed plus ax plus b, with a and b rational numbers. So these are elliptic curves of the rational numbers, q. And let us assume that actually these numbers are in z, because I soon want to go mod p on this equation. Look at a bar and b bar in z mod p, and then look at solutions over finite fields. So let us assume that these things are actually in z. So it turns out that the elliptic curve has a group structure, a set of solutions over any finite extension of Q or even infinite extension of Q, field extension as a group structure. It's a finitely generated abelian group. And I assume that all of you have seen this famous picture before. Something like this, where if you have 2 points on the elliptic curve P and Q, the sum is not the third point on the straight line joining P and Q, but it's, you drop a vertical line. So this is minus R. So another way to say it is that P plus Q plus R is 0. So P plus Q is minus R. It's this point down here. So this is the group law. If you have some coordinates for P and some coordinates for Q, you can obtain the coordinates for R by making this particular law explicit, geometric picture explicit. Okay, so it turns out that it's an abelian group. P plus Q is Q plus P, as you can see from this picture. The line is the same. And the remarkable thing is this is a finitely generated abelian group. Not remarkable perhaps, but it's now a very well-known fact, but there's finitely many generators. Okay, so there is an integer called the conductor of E, such that if L does not divide N, is again a prime, then, as I said, we want to reduce the elliptic curve mod P, or mod L, because P now is going to have some meaning later. So if L does not divide N, then E tilde, which is you just reduce A and B mod L, and then look at the solutions of the finite field FL. Now you have a finite many X and finitely many Y's. So it's also an elliptic curve because you're outside the conductor, so it's smooth. And you can speak of the number of solutions of this curve over the finite field FL. So if you count the number of solutions over the finite field, it's a finite number now, it may not be infinite like over Q. It turns out to be essentially L plus 1, because it's basically what? I mean, the number of solutions of on a line, they're basically L solutions on y equals mx plus c, right? Where m and c are in the finite field. For each x, there's a unique y. So L solutions, but you also have the point at infinity. So there are L plus 1 solutions if you were a line, but the elliptic curve is like a twisted line. So it's not really L plus 1. There's an error, and for some good reasons, you don't write plus the error, you write minus the error. So minus AL for the error. Okay, and then starting from these errors, one for each prime not dividing n, there's some recipes to come up with ANs for all n, where n equals 1 to infinity. Okay, so this is, notation is beginning to look very familiar because we also had some ANs for modular forms, and the remarkable thing is that if you take the Q expansion, then you actually get a genuine cusp form of level n is the conductor of the elliptic curve, and trivial Nabin-typus. Even a primitive cusp form. Okay, so let me give you one example. For example, if you look at the elliptic curve x naught 11. So what is x naught 11? So what is x naught n? X naught n is you just take the upper half plane and go modulo gamma naught n. So look at this fundamental domain. And then there's some cusps missing, so you compactify. You get a compact Riemann surface. Sometimes this has genus 0, sometimes genus 1, genus 2, etc. It has some holes in it, and you get an elliptic curve when the genus is 1. So the first time you get something of genus 1 is 11. Well, the first elliptic curve turns out to have conductor 11, and that's also the 11 here. Okay. And so this 11 now is becoming somewhat important, because if you try and look at elliptic curves for conductor 1, 2, 3, 4, 5, 6, 7 up to 10, then you will not find any elliptic curves of those conductors. But there's one of conductor 11, and here's an explicit way to see it. The upper half plane is appearing twice in this lecture, in different ways in this lecture. Okay. So far, there are no modular forms on this page yet, except here, but here there's no modular form. But it turns out that this is an elliptic curve. And the corresponding Q expansion is something very explicit. I would have written down the equation here for the elliptic curve, y squared equals something, but I don't remember it off the top of my head, and I haven't written it down here. So it's something very concrete, and you can look it up. And then let me tell you some very interesting coefficient, the 11th Fourier coefficient, q to the 11th. So it's something very concrete. These are the error terms A2, A3, A5, right? And then A4 is built out of A2 in some way, which I didn't quite tell you, but I said it can be done. Once you have the prime ones, then you get all the composite ones. And if you like modular forms, then you might recognize this in terms of the Dedekind eta function. So this particular modular form is something very concrete. Sorry, I'll write this again, maybe a bit later, but this is not so important. This is a side remark. So it's the product n equals 1 to infinity, 1 minus q to the n, and then q to the power 1 over 24. So this is a half integral weight form, as we saw in the last lecture. If you square it, it becomes weight 1. Square this is also weight 1. If you multiply these two, you get a weight 2 form. So this is a weight 2 form of level 11, and it's exactly this modular form. So this is not an explicit formula for it in terms of the Dedekind eta function. Okay, so please keep this modular form in mind, and keep these numbers in mind, because I'll be coming back to it very soon. And then the last example of a modular form that I want to give is the delta function, which came up in the last lecture, extensively studied by Ramanujan. So I get a chance to write the product a bit better this time. N equals 1 to infinity, 1 minus q to the n, very similar to what was there. 24th power of what I wrote over there. Okay, so that is how it's defined, maybe officially, or as in Professor Ramke's lecture in some other way. But in any case, all those formulas are the same. And what is important for us here is that it has a Q expansion where the Taylor coefficients, or the Fourier coefficients, are traditionally called tau of n. And I'll write a few down again. These are very famous numbers. There are entire theorems about these numbers. And I think one of Professor Ono's talks also deals with the non-vanishing of these numbers. One of the colloquia later, or last talks of the day, maybe Tuesday or Thursday. And if I hope you can see the last one here, 5, 3, 4, 6, 1, 2, I'll read it out. Q to the 11. I wanted to write one more here. Okay, so this modular form has also a Q expansion, and here are some explicit and very famous coefficients, or first few coefficients of the delta function. So this is a modular form of weight 12, as it turns out, and level 1, cusp form, level 1 and trivial lemma-typus. Okay, so now I want to look at what is at its p-stabilization. Okay.
Can you please slide down a bit?
Yeah, sorry. It's p-stabilization. Well, what do? By now you're more or less used to it. So you take a difference of two old forms, delta z and delta p z, but this time you factor the following polynomial for p is a prime. Whenever I write p-stabilization, p is a prime. So you look at the quadratic polynomial, x squared minus tau px plus p to the 11, all integer entries, and you factor it as x minus alpha, x minus beta. Okay, and let me assume that p does not divide tau p. Okay, so for example, for the first few primes here, p unfortunately does divide tau p, because 2 divides tau of 2, and 3 divides 252, and 5 divides 4830. But if you look at this 11th thing, then you can see that this 534612, if you divide by 11, the remainder is actually 1. 11 doesn't divide it. It's congruent to 1 mod 11. So there are some primes, these are called ordinary primes, for which this condition holds. And then when you factor this, then one of these will be a p-adic unit root and the other will not be. So let us assume that this is the unit root, that's p-adic valuation 0, and this one doesn't, has positive valuation, and that's the one that I throw in here. Okay. So it turns out that this is also a cusp form, but now because of the p-stabilization, you've added p to the level. And we get a modular form of weight 12, level p, and trivial Neyman typus. And maybe I will write its Q expansion down if I can find it. Well, it's exactly the same as the other one. So it is Q minus 24Q squared. You see the Q expansion doesn't change much, it only changes at P. So exactly the same as the other one, but what happens at the 11th one is, the 11th Fourier coefficient, you get alpha times Q to the 11. Okay, this number alpha, which was the root of this, you get that. Okay, so this is the Q expansion. Exactly the same as before, except at the primes where 11 divides n, there's a slight change. For example, at Q11, you get alpha. Okay, so very good. So these are some kinds of modular forms that one wants to introduce. Now, let me talk about congruences. So let me go back to the Eisenstein series. Okay, and then I'll come back to these cusp forms. So look at the p-stabilization E2p, which was zeta p minus 1 divided by 2 plus sum n equals 1 to infinity sigma 1 np q to the n. If you remember, there were some p-deprived Dirichlet L function here, but this is what it stabilizes to. And there were even formulas for this. This was minus 1 minus p b2 over 4, which if you look up the literature for the Bernoulli number, second Bernoulli number is this. And let us also look at the p-stabilized Eisenstein series of weight 12. And you get this Q expansion. Right, k minus 1, so sigma k minus 1, the weight is 12 now, so sigma 11, p deprived n, q to the n, which, if you look up the general formulas I wrote down a couple of pages ago, looks like this. And this now, if you look up the 12th Bernoulli number, it's minus 691 over 2730. So the two minus signs become a plus sign. '24 is there. 2730. Okay, so we have these two Eisenstein series, which are p-stabilized. And now something rather remarkable happens. So I'm going to fix p to be 11 again now. Well, one thing to notice immediately is that D11 by Fermat's little theorem is the same as D, right? For all integers D, in particular the ones coprime to P. So this says that sigma 11 of n E is
Can you please slide up a bit? Sorry.
Yeah, sorry.
Thanks.
Yeah, sigma 11 of P of n is sigma 1 of P of n. Right? At least mod P. Why? Because this is the 11th powers of the divisors of n, and this was the 11th powers of the divisors, the first powers of the divisors of n, and both of these for D coprime to P. And so when you sum up, each of them individually are congruent, so you get that. So this is saying that this Fourier coefficient is congruent to this Fourier coefficient mod 11. Okay, so this is one remark. But here's something even more remarkable. When P is equal to 11, if you compare these two numbers, this number and this number, and if you try and go mod P, what's going to happen? Well, mod P, this 1 minus P just becomes 1. And this 1 minus P 11 also becomes 1. So what are you left with? You're left with minus 1. You're left with minus 1. And you're left with a 691 over 24. Sorry, there's 24 on both sides, I think. So the 24s will cancel. You're left with this. This is a question mark. Whether this is true mod 11 is 11. And remarkably, this is true because if you cross multiply, this becomes minus 2730. And if you bring it over to this side, you will get 3421. So this is actually a check because 11 divides 3421. Okay, so that's you add 2730 to 691, you get 3421 and 11 divides it. So you have this congruence here. Okay, mod P equals 11. So the constant terms are also congruent mod P to the 11. So what do we conclude from this? We conclude that symbolically we write E12 of P, let's take the larger weight one first, is congruent to E2 of P mod P for P is equal to 11. Is everyone following this up to this point? I tried to do it extremely slowly to write this congruence down. I could have said this line almost immediately, but I really showed you how each Fourier coefficient was congruent for n greater than or equal to 1. And then I spent some time also on the constant terms, A0. And they were also congruent 1, mod 11. So we just write that the formal Q expansions are congruent mod 11. So these are forms of weight 2 and weight 11. In fact, here is something even more remarkable. There exists modular forms Fk, not just a weight 2 and weight 11, which looks very special, but one of every weight. But unfortunately, the Nabin-Typist character is not trivial. These two forms have trivial Nabin-Typist character, Dirichlet character. But you have to put a rotating Dirichlet character here for chi, and let me just recall quickly what this is. This is the mod p cycloatomic character. So it's a Dirichlet character of conductor P. Okay, and it basically takes values in the p minus first roots of unity. You know, this group is basically z mod p minus 1 and cyclic. And so this should make a lot of sense to you. But the root of unity you choose here is quite canonical. It is the root of unity such that mod p, you get the original number a here. So let me not go too much into it. But there's just some Dirichlet character called the mod p cycloatomic character, such that all the modular forms, F1 is congruent to F2, is congruent to F3, is congruent to F12, is congruent to so on and so forth, mod p. And E2 was, F2 was E2p, F12 was E12p, but there's one for every weight. And so this is really, really rather remarkable that there are these Eisenstein series. Sorry, this is not right. There are Eisenstein series. I should not write S here. I should write M. Because they're actually modular forms. They have some Q expansion. Sorry, they don't vanish at infinity. So MK E omega 2 minus K. Yeah, so there's one modular form of every weight, and they're all congruent mod p equals 11. So this is one sort of example in the congruences. Okay, we talked about E2 and E12 and how they all became congruent. But here is another one with the elliptic curves and the delta function, which is equally remarkable. Let me talk about that now. But before I do that, how much time do I have, by the way, Anupam? 10 minutes?
$45 minutes, almost 40.
No, how much time do I have left?
40 minutes.
40 minutes?
Yep.
Oh, wow, I'm going way too fast. Okay, for some reason, you know, these lectures that start at 15 and finish at 45, I always get very confused. Okay, so I have to finish at 12:45.
Yes, yes.
Oh, great, great. I can slow down.
90 minutes talk.
1.5 hour talk, right?
Yeah.
Yeah, okay. So I'm going way too fast. I hope, should I pause a little bit for the Eisenstein series congruences? Was it okay? I think I went slowly there.
I think it is fine.
Fine? Okay.
Yeah.
So I'll go a little bit more slowly in the next part. And let me then give you, I was not planning to do this, but since I have time, let me give you a dimension table for the space of cusp forms. So remember, we already talked about, let me call it F2. F2 was the modular form attached to X011, the elliptic curve. And we wrote down some Q expansion. And maybe I'll call it F12 because of the notation that's about to become obvious in a second, for the p-stabilized delta function for p equals 11. We had some modular forms, some cusp forms of various weights. This one was in S2 11 1, and this one was in S12 11 1. One was a weight 2 and one was a weight 12, and just like these Eisenstein series, weight 2 and weight 12, and the level was 11. Now these are just some particular modular forms. Let us back up a little bit and make a table of all levels and weights, cusp forms of all levels and weights. Okay. So these are the levels, level 1, level 2, level 3. Now, as I said, if you go to weight 2, there are no elliptic curves of conductor less than 11. And it turns out, so in particular, there are no modular forms corresponding to elliptic curves of conductor like 11. And in fact, there are no modular forms at all. Not all modular forms of weight 2 have to come from elliptic curves. More generally, they can come from abelian varieties, which I haven't talked about here, but they're similar geometric objects. But it turns out there are no abelian varieties also. So the dimensions, the space, the dimension of the space of cusp forms of weight 2 in level 1, weight 2 in level 2, weight 2 in level 3, so on and so forth, up to weight 2 in level 10 are all 0. And then suddenly, there's this elliptic curve at level 11. Then again, you get a bunch of zeros at conductor 12 and conductor 13. And then at conductor 14, it turns out there's another elliptic curve. And there's another elliptic curve, so on and so forth. Okay, so this is just numerical data coming from the space of modular forms, from the theory of elliptic curves and abelian varieties and modular forms. So let us go to weight 4, where it's not elliptic curves anymore, but you can use various things like the Riemann-Roch formula from algebraic geometry to compute the space of cusp forms of weight 4 and various levels. And again, you get, for small levels, there are no, like everybody knows, for weight 4 and level 1, there's no cusp form of weight 4. So, but at weight 5 there is, weight 6 there is, 7, 8, 9 there is, and then it starts increasing. Maybe I'll write a few numbers here. 3 is with the 13, and then the 4. Sorry, it's not completely aligned. 3 should be under that 0. Okay, and then, by the way, the weight has to be even, right? Because the parity of the character has to match the parity of the weight. I took the trivial character. So let's go to weight 6. And again, no modular forms of weight 6 and small level, but then you do get some from level 3 onwards. Weight 8, 0, 1, 1, 2, so on and so forth. Weight 10, 0, 1, 2, so on and so forth. Weight 12. This is the thing that I really wanted to emphasize. For level 1, you got a bunch of zeros. There were no modular forms of small weight. Weight 2, weight 4, weight 6, weight 8, 10. There were no modular forms, but suddenly there was a modular form of weight 12, and that is, of course, and then you start getting. Does anyone want to finish that sentence? So I know people are paying attention. What is this cusp form here? I didn't finish the sentence. There's a 1 here in terms of the modular forms that I wrote down. They're even on this page.
Ramanujan's delta function.
That's the delta function here, right? So that's the delta function, and that's the elliptic curve x0 11. And then you get some of the modular forms here of level 1 and higher weights, right? As you go down here. Now here, you know, there's some arguments in the form, in the world of modular forms, or if they aren't, let me make them up. You may ask, what is the first modular form? Is it this one? There's after all a bunch of zeros and then a 1, or is it this one? Bunch of zeros and then a 1. Which should be the first modular form? Well, there are people who only work in weight 2 and they say it's this one, and there are people who only work in level 1 and they say it's this one. But fortunately, for people who work in all weights and all levels at the same time, you don't really have to settle this argument because of something which is rather remarkable. This is the first cusp form of weight k equals 2, and it's x0. The modular form corresponding to the elliptic curve. And here's the first modular form. First, according to some people, first cusp form of level n equals 1. And of course, it's the delta function. Maybe I won't call it F12, sorry, because F12 is the p-stabilization.
Can you please slide up a bit?
Yes.
Thanks.
So let me repeat. You have these two cusp forms here. Some people say that this should be the first cusp form because it has, it's coming at the level, the weight is 2, but the level is changing. And so it's the first, it's the smallest level form of weight 2. Some people would say this is the first cusp form. But remarkably, these two are related. So you don't really have to say which is first. In some sense, they're part of the same family. So these two cousins are actually, these two modular forms are actually cousins, part of the same family. These two are related. Okay, so why are these two related? Well, they're related by a congruence. Congruence mod p equals 11. So the number p equals 11 is coming up again and again. It came up here because the conductor was 11. It didn't really come up here, but I took the 11 stabilization of this form and I called it F12. Okay, so it also indirectly came up here. It also does come up here actually quite directly because 11 is the first prime for which, just like 11 is the first conductor here, 11 is the first prime for which p does not divide tau of p. If you remember the Fourier coefficients, tau of 2 was 24, that's even, so 2 divides 24, no good. And 252, tau of 3 was 252, 3 divides that. 4830, tau of 5, 5 divides that. Similarly, tau of 7 divides tau of 7, but 11 is the first prime for which 11 did not divide tau of 11. So 11 is quite special for this modular form also, for the delta function. 11 was, of course, very special for this elliptic curve. It was its conductor. So, and 11 is also very special in the sense that it gives a congruence. And here is what I want to get at now. This is perhaps the most important part of the talk. That even though 11 is individually important to each of those guys, they're connected by a congruence, which is also involves the number 11. So of course, tau 1, right, for n equals 1. I won't write the n's here. I'm writing the n's here on the side here. For n equals 2, this is minus 24. And if you go back to that Q expansion I wrote down, it's minus 2, right? And these are, of course, congruent minus 11. If you add that there, you get 22. Tau of 3 is 252. And A3 for the elliptic curve was, sorry, I've already added the minus 1 in my head, 252. And if you add that, then 253 is divided by 11, right? 22, and then 33. That's divided by 11, and so on and so forth. For example, let me do a few more. Minus 1472 is congruent to 2 mod 11, and 4830 is congruent to 1 mod 11. Let's check these out. N equals 4, n equals 5, and n equals 6 I won't do, but if you go down to n equals 11, then if you remember there was a 5, 3, 4, 6, 1, 2, and this is actually 1 mod 11, which is also the A2, sorry, the A11 coefficient for the elliptic curve, the modular form of weight 2. Okay, so all the Fourier coefficients of the two modular forms are congruent modulo 11, and I didn't actually look at the delta function. I looked at the p-stabilization of the delta function, but even the number alpha that you got for the 11th Fourier coefficient for the p-stabilization, even that turns out to be 1 mod 11. So that doesn't change much. So most of the Fourier coefficients anyway were the same, but the 11th one is also the same. Sorry, the 11th one changes, but it's congruent to 1 modulo 11. Okay, so we can summarize all of this now by this remarkable observation that 11 is related to both the two so-called cusp forms, not just individually, but by this congruence. I.e., we obtain the following congruence. Delta 11 or delta P, P is 11, is congruent to F X0 11. This is F12, what I call the F12. This is what I call the F2. Mod P is 11. Okay, so the P stabilization of the delta function and the P stable, and there's no P stabilization here because 11 was already in the level, so I didn't have to P stabilize, but this was level 1, so I had to P stabilize. These two modular forms are actually congruent modulo 11. And now you can guess what's going to happen. In fact, there exists a cusp form. This time it's really a cusp form, not a modular form, of every weight. Let me start with weight 2 though here. Such that F2 is congruent to F3, is congruent to so on and so forth. F12, remember F12 was the P stabilization of delta, F2 was F of X0 11, that modular form for that elliptic curve. Mod P. All these modular forms, which have some strange Q expansions, and the Q expansions may involve some algebraic numbers, not just algebraic integers, not just regular integers, but some algebraic integers. For example, this alpha, for instance.
Can you please slide up with it?
Sorry, yeah. All these modular forms are going to be congruent modulo P. So I want you to think a little bit about this remarkable thing. So for the Eisenstein series, maybe you were not so impressed because the Eisenstein series had some Q expansions, which are quite concrete. It was quite impressive that the A0 terms got congruent modulo 11, and but maybe not so impressive that the other Fourier coefficients were congruent modulo 11. But here, you really see some genuine congruences for the cusp forms, Fourier coefficients for these two cusp forms. They're turning out to be congruent modulo 11. And this is really, really rather a remarkable thing that all these cusp forms are congruent mod 11. So we shall say the collection of cusp forms or modular forms in the previous case for the Eisenstein series. Let me just say forms so that I include the previous example. Collection of modular forms or cusp forms in this case. Fk for k equals 2 to infinity, and in the previous case for the Eisenstein series it was even 1 to infinity, but let me, for reasons that will become clear in the next lectures, start from weight 2. Form what is called a p-adic family of modular or cusp forms. Okay, so these are two examples. What we've done so far today are just, and this was supposed to be a motivational lecture, though I didn't tell you at the beginning. I thought I'll do one lecture where I'll motivate things with two examples and do them properly. So these are two examples of p-adic families of cusp forms or modular forms. Eisenstein family was the first one, and the second one was the p-adic family, which is passing through the delta function for p equals 11. And in weight 2, it was just giving the first elliptic curve. In weight 12, it was the p stabilization of the delta function. But there's one for every weight. Okay, so thank you. I think I still have 15-20 minutes, which is good news because I'll go much slower the next time. But let's spend maybe 5-10 minutes on some questions. Before you ask, maybe I'll say that in the next lecture, I will give the formal definition of a lambda-adic form. And I will also give you the formal definition of the lambda-adic Eisenstein series, a formal definition of the family. Here I did it with some Q expansions and things, but I will give more formal definitions, and I'll in particular define what a lambda-adic form is. It hasn't really come up today. But the lambda-adic form is almost the same thing as the p-adic family of modular forecast forms. So I'll define that the next time. And then in the third lecture, I will give some theorems about the finite generation of the space of lambda-adic forms. It's not at all clear when I define lambda-adic forms that this, not the vector space this time, but you get some lambda module. Lambda is a power series ring over ZP in one variable. That's finitely generated as a lambda module. That's not so clear. So I'll try and motivate that and some other facts about lambda-adic forms. And then in the last lecture, I will speak about Galois representations, as I said. Okay, I'll stop here. So, any questions?
So is it like that for any cast form you have, you can have these families as long as this ordinary condition is required for that, or?
Yes, so I didn't make a big fuss about the ordinary condition, but in the theory of lambda-adic forms, the theory of families is only for the ordinary cases. So in the theory of lambda-adic forms, there will be an ordinary condition. And so that is a good question. Let us just look back at some of the Q expansions. So for example, if you look at the p-th coefficient of Ek chi, here it is.
Yeah.
Okay. So by default, you only take divisors for, you can't see my finger probably. Okay, let me push this in. By default, you only take divisors for d dividing it with d co-prime to p. So what is the p-th Fourier coefficient going to be here? Well, if n is p, then no divisor, right? You only, except for d equals 1, there's nothing co-prime to p because the only divisors are 1 and p. So you'll get chi 1 and 1 together. So it'll be 1. So the p-th Fourier coefficient will be 1, which of course is a p-adic unit. P does not divide 1. And similarly, if you go to some of the other Q expansions, for example, for this elliptic curve here, the 11th Fourier coefficient, by the way, for elliptic curve of semi-stable reduction, where 11 exactly divides the level, you know that AP is plus minus 1. So it turns out to be 1 here, but in either case, it's plus minus 1. And so this particular elliptic curve also has ordinary, it's ordinary. 11 does not divide 1. So that modular form is also ordinary. And of course, finally, for the delta function and its p-stabilization, the Q expansion at 11 has alpha as the Fourier coefficient, and we took the unit root. So 11 again does not divide alpha, or the p-adic 11-adic valuation of alpha more precisely, because alpha is not an integer anymore, but the 11-adic valuation of alpha is not positive, it's 0, so it's a unit. So all these forms that I wrote here were 11 ordinary. And this whole theory is going to work, all these modular forms in this family, they're going to work for, sorry, all these modular forms in this family are all going to be ordinary. There is a theory for non-ordinary forms, which is due to Coleman, and it is extremely interesting. It involves some p-adic Banach spaces and things, but is a little beyond the scope of this course. It involves some rigid analysis. So I won't get into that in this course. That's a separate course, perhaps, for another time.
And can we have a look at the table that you gave for weight and this thing?
Sure.
That
Yes.
no, that table of modular forms that where the first one is appearing, this one.
Yes.
So you said even for corresponding to abelian varieties, we will not get modular forms where we are having 0. So you said something. So I just want.
Yeah. So it turns out that these zeros are not just because there are no elliptic curves of conductor less than 11, But in fact, more generally, there are no abelian varieties of conductor less than 11. Because these modular forms of weight 2 in general don't only correspond to elliptic curves. The ones who correspond to elliptic curves are the ones whose Fourier coefficients are integers or rational numbers. But if the Fourier coefficients are algebraic integers or algebraic numbers, then you will have an abelian variety of higher dimension, not dimension 1. Elliptic curve is an abelian variety of dimension 1. So you'll have abelian varieties of higher dimension. For example, you may get your Q expansion in Q root 5. That's a very common field of Fourier coefficients. In that case, the weight 2 form that you get is not an elliptic curve, but it turns out to be an abelian surface. So it's a 2-dimensional abelian variety. And it turns out that Q root 5 is actually acting on the abelian surface as endomorphisms of the abelian surface. And in more general, you can have abelian varieties of higher dimension. And all of this is very classical and very old. It goes back, it's very well described, for example, in Shimura's book. And I'll list some of the references maybe in the last talk. Shimura's pink book in Princeton University Press, pink and black book, 1971 perhaps, which may have come up also in Professor Ramke's talk. That book has a very nice exposition of all these abelian varieties and elliptic curves coming from weight 2 forms. They're quotients of Jacobians of modular curves. So that explains all these zeros here.
Okay, thank you. Thank you so much. Any question from anyone else?
Hello.
Yes.
Hello, sir. Yeah. So, sir, I actually, I'm pretty much new to this field of modular forms, and I have been studying it by myself for the past 1 or 2 months. So I wanted to have a little bit of idea about what a cusp actually is, like from the visualization point of view and that stuff. So can you explain a little bit about that?
So your question is, what is a cusp form actually?
Yeah, like I know the definition point, from the definition point of view, it's a modular form and all that, but like there's a certain kind of visualization kind of thing, right? So can you tell me about it? Yeah.
Forms, they show up in many ways. For one way is that their Fourier coefficients encode geometric data. For example, the cusp form attached to the elliptic curve, the Fourier coefficients encode the error to the number of points mod L, the L Fourier coefficients. So that's one way to look at it. There are various ways to I'll give you another way. If you take a cusp form of weight 2, and if you look at the differential form f of z dz, where f is the form of weight 2, it forms a differential form on H mod gamma naught n, that particular Riemann surface, that particular open Riemann surface, it forms a differential. And the reason that it's not just on H, but on H mod gamma, or gamma naught n, is because F satisfies the right automorphy property. F of gamma z is Cz plus d squared F of z. Let's assume that Newton type is trivial. So that automorphy property, along with the corresponding automorphy property for dz, the differential, combines nicely to give you a differential form on the quotient. So you could think of weight 2 forms as differentials, if that makes it a little clearer to you. That is actually the way that the space of dimensions of modular forms are computed, because you compute the space of differential forms using algebraic geometry, Riemann-Roch theorem and things. But ultimately, it's just a holomorphic function on the upper half plane with lots of symmetries. And when it's a primitive form, it encodes, the Fourier coefficients encode very interesting number theoretic data.
Okay, thank you, sir. And from the point of view of singularities that we are looking into,
Yes,
from that point of view, how do you see it?
Singularities. Yeah, so the cusp form just vanishes at the cusps. And if you look at the differential form in terms of like the dz, if you look at it in terms of q, if you look at f of q, then the differential form actually turns out to be f of q dq over q. So it is very important that the Q expansion starts with the first term, A1, and not A0, because you want to cut out the Q, cancel the two Qs to get something which is a genuine differential form. So I don't know if this is answering your question, but it's the cusp forms which give differentials. If you give a modular form and do f of z dz, you won't get a holomorphic differential because it'll be some A naught over Q. So that is some little exercise you should try and do. And that is why it's really the cusp forms that give genuine differentials, holomorphic differentials. They're cusp forms, but they're giving holomorphic differentials, not cuspal differentials, holomorphic differentials.
Okay. Thank you so much.
Yeah, yeah. I see on the YouTube there's some lots of comments, so not lots, but a few. So people are complaining that it's not visible, but hopefully that got corrected because of Anupam's interventions. And
okay, we'll look into that. Yeah.
There's some other question on YouTube about, is the family there only for p equals 11 or for any prime p? So the Eisenstein family is there for any prime p, but I chose p equals 11 to fix ideas. But the family passing through the delta function, the p-adic family passing through the delta function, is only there for p equals 11. In fact, it's there for any prime p such that p does not divide tau of p, so what is called an ordinary prime. And 11 is the smallest one. And as I said, for the primes 2, 3, 5, 7, there is some family passing through the delta function, but it may not hit forms of weight 2, weight 3, 4, 5, small weights. The theory is only very, very nice when you have an ordinary prime. But yeah, there are Coleman families also passing through these modular forms. Right now, we're only talking about Hida families or lambda-adic forms.
And is it correct to say that every cusp form has to come from some abelian varieties? Is it correct?
Yes. In weight 2, it's true. In weight 2, it's true that every abelian, well, not every abelian variety, but what is called a abelian variety, you put enough necessary conditions on your abelian variety to guarantee that they come from cusp forms. So, abelian varieties have rings of multiplication. For example, elliptic curves can have complex multiplication. Abelian varieties have more general multiplications. It may not be a complex field that's acting, but in general, you have either a totally real field or a CM field acting on your abelian variety. And anyway, so when you have a number field acting on your abelian variety as endomorphisms, if the dimension of the abelian variety matches with the degree of the number field over Q, then you say that your abelian variety is of GL2 type. These are the next most complicated abelian varieties, or next simplest, I should say. They're not the most simple. The most simple abelian varieties are the complex multiplication abelian varieties. They have fields of endomorphism, number fields acting, which is twice the dimension of the abelian variety. But sometimes only the dimension of the abelian variety number field acts on the abelian variety. And those are called of GL2 type. And it turns out that, that every abelian variety over Q of GL2 type is modular. So it comes from a modular form of weight 2. And the more explicit connection is that the zeta function of the abelian variety involves some L functions, and the L functions are exactly the L functions attached to the modular form that showed up in Professor Ranke's talk. So that's the more explicit connection by the zeta functions. I did it a bit naively here by just saying that the ALs for the elliptic curve were the ALs for the modular form. But a more formal statement would have been that the L function of the elliptic curve is exactly the L function of the cusp form. So similar statement holds for the abelian varieties.
Yeah, thanks. So if there are no other questions, then you can thank the speaker.